Hey everybody, Chris McClure here. We are now going to talk about variation and what that really means is discussing how two variables, in particular the x and y variables, but it could be in between any two variables, s and t, G and F or whatever. We'll just use X and Y. Typically, we'll use Y written as a function of X. Okay? But it doesn't always have to be that way. Okay? All right, moving along here. Now, there are going to be a handful of special relationships that we're talking about when we're talking about variation. The first special relationship that we're going to talk about is probably the most simple, and we're talking about direct variation. Direct. Meaning how one variable varies directly with another variable. You increase one variable and the other variable increases in a nice linear fashion. If x is 0, y is 0. If x goes up by 2, then y goes up by 4 or whatever. And if x goes up by 4, then y will go up by 8. That sort of thing is very predictable and it's simple. So here's what it looks like to have direct variation. Or in other words, one variable is directly proportional to the other variable. And this is the sort of equation that we would look like. We would say that one variable, in this case y, is equal to some constant multiple of the other variable, in this case x. And we'll use k as that constant of proportionality. We won't know what k is until we're given some information. All right, and of course, k would be the slope of the line, which would be the graph of this equation. Of course, we're assuming that k is positive in the context of the problems in this section, but I'll also tell you that we could have situations where k could be negative. So in that case, we would say something like the y is negatively directly proportional to x and so forth. But for most of the problems that you'll do, if not all, involving direct proportionality or direct variance, k or your constant of proportionality will be positive. So let's take a look at a quick example, and I think this example is in your textbook. So suppose that we have a mortgage, right? You know what a mortgage is? I think most of you do. Mortgage is basically a home loan. It's a loan for the express purpose of financing the purchase of some real estate, usually a house and or some property. So we're going to make a monthly payment, and the payment amount, P, as in P dollars, this payment amount on this mortgage varies directly with the amount borrowed, B. So you borrow, say, so many thousands of dollars, B, and you can very easily figure out what your monthly payment is because there's a direct relationship. So suppose that we've got a monthly payment on a 30-year mortgage, and we're told that the payment is going to be $5.95 for every $1,000 borrowed. That is the relationship. So if you know how many thousands of dollars you borrowed as the principal, you take that number of $1,000 and you can just apply that to the 595. So let's go ahead and figure out a formula that will relate the payment amount to the amount borrowed. And then once we figure out that relationship, then we'll answer this question: what is the monthly payment when the amount borrowed is $125,000? All right, let's take a look here. There's a direct relationship between those two variables, payment amount and the amount borrowed. Okay, now we're told that there's $5.95 that would be the payment for every $1,000 borrowed. So if you borrow $1,000, then your payment is $5.95. So plug those two numbers in. Plug those two numbers into the equation, and then solve for k. So you have 5.95 is equal to k times 1,000. Solve for k by dividing both sides by 1,000. And of course, 5.95 divided by 1,000 is 0.00595. And now you have a new equation where p is equal to this value of k, 0.00595, times b. Remember what b is. B is the amount borrowed. So now we're going to put 125,000 in for B. And sorry, I know that this is a little bit screwed up. And then solve for P. So we have 0.00595 times 125,000. And that is equal to 743.75. Okay? All right, now let's talk about a different relationship between two variables, and this relationship is inverse variation, as in one variable is inversely related to the other variable, or there is an inverse sort of variation between the two variables. And this is what it looks like. Here we say y varies inversely with x, which is actually the same thing as saying x varies indirectly with y, because in this equation you could multiply both sides by x and divide both sides by y, and you'd have this really the similar sort of equation. Anyway, but it's customary for us to have y to the left and our expression involving x to the right. Now here's what the graph looks like. Of course, the specific shape of it will depend on k. But here's the overall shape of what it is. There's no intercepts. Y is never going to be 0, and x is never going to be 0 in this sort of equation. And of course, we'll only address the specific case where k is positive. In this case, here's an example of inverse proportionality. So you know that a piece of board, wood board, that the longer it is, the less weight that it could support in the middle. No matter how thick the wood is, the longer it is, the less that it could support. So here's, we've got a piece of wood here. It's a board that that connects two edges of the canyon. Now, you're going to walk across this board. Is it going to hold you? Well, let's answer this question. Now, we have this relationship between maximum weight that the board can hold. In fact, this is a 2" by 4" a 2x4 of pine, that the maximum W will vary inversely with its length. So here's what that relationship looks like, where the maximum weight varies inversely with its length. And we need to solve for k. So in these problems, you'll always be given some information That will allow you to solve for K. Basically, they'll tell you for a specific length what the maximum weight is for this problem, for example. And in particular, we're told that if you have a 10-foot length piece of board, that it can support 500 pounds. So guess what? You'll plug in 10 foot for L and 500 pounds for W. Okay? And then you'll solve for K by multiplying both sides by 10. And now you have that constant of inverse proportionality for K. So now you have the equation W is equal to 500, or excuse me, 5,000 over L. So now we can answer the question, find the maximum weight that can be safely supported by a length of 25 feet. So if this piece of wood that satisfies this equation right here is 25 feet, will it support you? Well, you plug in 25 feet for L in the equation, and then 5,000 divided by 25 works out to be 200. So the answer to this question is depends. It depends on how much you weigh. If you weigh over 200 pounds, then it's not going to support you. If you're under 200 pounds, then it will support you. Now, will it support you if you're exactly 200 pounds? Well, theoretically, yes. But, of course, the longer it is, the less weight it's going to support. All right, moving along here. Now let's talk about joint variation / combined variation, where we are bringing in more than one variable besides x on the right-hand side of the equation. Or we might have a square or cube or square root or something of one of the variables. So let's take a look at this example to see what we're doing here. Here we've got the loss of heat through a wall. It varies jointly with the area of the wall and the difference between the inside and outside temperatures. So you've got a wall, and it might be super cold on one side and super hot on the other. And the difference between those two temperatures is going to be one of the variables. And the area of the wall will be another variable. And then we have inverse variation with the thickness of the wall. So we have four variables going on here. We have the heat loss, L. We have the area of the wall, A. Temperature difference, T. And we're going to let D be equal to the thickness of the wall. Now let's reread this equation. The loss of heat through a wall varies jointly. So there is a direct proportionality between loss of heat for both the area of the wall and for the difference in the temperatures. And then there's that inverse relationship with the thickness of the wall. So let's see what the equation would look like. And here it is. We have the heat loss, this heat loss right here. It varies jointly. So here's that constant multiple. And so you notice up here, there's both the area and the temperature difference. So when we say that the heat loss varies jointly with area and temperature difference, this is what we mean. Is that L is directly proportional with both of them. So you just multiply those two variables together. And then there's the inverse variance with the thickness of the wall. The thicker the wall, the less the heat loss. The smaller the thickness, the thinner the wall, the more the heat loss. So no wonder of this relationship. But of course, the area of the wall, if it's a larger area wall, there will be more heat loss. Less area means less heat loss. Same thing with the temperature difference. If there's a smaller temperature difference, there will be less heat loss. If there's a larger temperature difference, then there will be more heat loss. So these relationships make sense. So we now need some information to solve for K. If we were to do something useful with this equation, they might give us, say, hey, suppose that we have the area of this wall is so many square feet, and the temperature difference is this amount, and the thickness of the wall is so many, and that the heat loss is so much. And so for those 4 pieces of data, then we could solve for K and then answer some useful questions. All right, let's do yet another example where we have combined variance. So this one has to do with the relationship between the force of wind on a flat surface at right angle to the direction of the wind. That the relationship between that force and the area of the surface and the square of the speed of the wind. So let's go ahead and take a look at that relationship. Here we've got force is equal to some constant multiple K times the area of that surface, whether that's a wall or a door or a window or whatever, and then times the speed squared. Remember, V is velocity, which is the same as speed squared. Okay. So, in order for us to answer the question, which is the last statement at the end of the paragraph here, we need to know what K is. So, of course, as with all the other problems, we are given just enough information to solve for K. We're told that a wind of 30 miles per hour blowing on the window, measuring 4 foot by 5 foot, has a force of 150 pounds. So let's plug in those numbers into our equation. Here's the 150 pounds for F. And the area of that window is 4 by 5, which is 20 square feet. And that speed was 30 miles per hour squared. So we have 20 times 30 squared, and then take 150 divided by that. So you have 150 is equal to 18,000 K. Divide both sides by 18,000. You got 120. 1 over 120, I should say. Okay. So now you plug in a 1 over 120 in for K into the original equation. So there it is. And then to answer this follow-up question, what is the force on a window measuring 2 by 3 feet caused by a wind of 70 miles per hour? Well, you plug in the area, which is 2 times 3 is 6, right there. That's for A. And the speed is 70, so you plug that in there. And, of course, K is 1 over 120. So you got 70 squared times 6 times 1 over 120. And that works out to be 245. As in, the force that is felt by that window when, it has the measurement of 2 by 3 feet, and the wind is 70 miles per hour, that force is 245 pounds. That'd be almost like me sitting on it. So anyway, so that's it for this section, and that's actually it for chapter 2. So guess what, folks? In addition to finishing the homework for this section, you will now be up for a quiz on chapter 2, your third quiz. So I'll be posting that later this evening after I get done posting this lecture. And then some of you have been asking, when exactly will I be putting out the tests? Well, I haven't even really started thinking about that, because I'm not going to be able to actually create your test until after I get back from my trip. Okay, so, but if I had to nail a time frame down right now let's take a look at the calendar here. So here we are on June 19th. I won't get back to town and get home until June 28th. I'm going to spend this weekend, the 29th and 30th, at home. I'll be back to work on Monday, the 1st. Remember, the 4th is a holiday. But early this week, though, one of my big ticket items is to create your test. So let's just say that I'm going to try by July 3rd to start putting out those tests, okay? That would be my best guess. And of course, for those of you taking the test not on a DMAT campus, I will email your exam to your proctor. Make sure, for those of you who are taking the test not on a DMAT campus, that I get your proctoring. Some of you I've already gotten them, but some of you I'm still waiting on them. And if I don't get your proctoring, then form, you're going to have to take it at a DMAT campus. Okay, you have really no choice. And then I'll also be sending out an email early this week of July 1st and 2nd, asking everyone in the class who's taking the test at a DMAT campus, what campus. So I know how many exams to send to each campus. Does that sound good? I would have to send those exams out by the intra-campus mail, so it might take a couple days to get out to Carroll, for example. Maybe one day to get out to Newton or West or Urban or whatever. All right, so just understand that. And then I will probably give you about a week, maybe 10 days to get the exam done. Okay? And so you'll have some flexibility. And then some of you have been asking, well, what about the final exam? Well, the final exam will be done during this time frame, late July, early August, okay? So sometime during this week right here. Same arrangement with your proctor or at a DMAT campus, okay? So, but I will ask you to have your final exam done and taken by Friday, July 2nd. August 2nd, I should say. But we'll cross that bridge for the final exam later on, of course, in July, mid to late July. But I know some of you have lots of questions, and that's okay. But I will also encourage you just to, focus on what you have in front of you. Just do the best that you can with the homework, and and doing the quizzes. I saw some of you did not take the Chapter R quiz, even after I gave a 2-day extension on it. So I don't know what the answer is, folks. Some of you have voiced concerns about, hey, I gave a quiz in a Blackboard using that link in that folder called quizzes, and you got screwed up on the due dates. Well, hopefully you've got that sorted out now of when the due date is for upcoming quizzes. And because I don't give quizzes using my math lab. Maybe I will in the future from some other class, but for this class, your quizzes are done through Blackboard. So make sure that you manage those due dates. Okay? So I'm going to stop recording now and work on getting your this video posted and working on the quiz. Okay? So you all have a good night. I'll see you next time. And take care.